Krizka, who's going to tell us about Dixmier sheets and associated varieties of affine algebras.
Yeah. Thank you. So it's a joint work with Tomoyuki, Arakawa, and Slava Futorny. And it's a work in progress, but I hope it will soon, well, it's almost done, it will soon probably on archive in a couple of weeks. Well, so I would like, well, I will give some examples that closures of Dixmier sheets may appear as associated variety of some simple affine vertex algebra, and also I'll give new examples of quasi-less affine vertex algebras for non-admissible levels. And because of the previous talk, I don't need to give much definitions because almost everything was done. But I will write at least something. So V will be some positively graded vertex algebra. And because vertex algebra is usually quite complicated object, so it's better to, well, if you want to do some representation theory or some other things, so then it's better to assign something which is a little bit more simple and keep some information. So we can assign, well, something what is called W-algebras. So it's an associate. Is it better? So use algebra, which is an associative algebra, and in fact, it controls the representation theory of vertex algebra. So if you want to describe all simple positive energy representations, then in effect there is a one-to-one correspondence with representation, simple representations of this algebra. I will need some mapping, so which goes, there is a canonical mapping going from vertex algebra to this algebra. And, well, also I will, well, there is a one map going from vertex algebra to algebra, to associative algebras. So the question is if there is a possible way how to assign to an associative algebra some vertex algebra. So this is called chiralization. And, well, as usual, it's quite hard to assign some associative algebra vertex algebra. And it's not unique. So the other invariant of a vertex algebra, it's again another algebra, which is called C2 algebra. And there is also a mapping, which I will denote by sigma Ju, going from vertex algebra to this Ju C2 algebra. This algebra it's Poisson algebra, and because it's commutative, so we can assign spectrum and maximal spectrum. So this x tilde will be spectrum, so which is called the associated scheme of vertex algebra V, and also we can assign variety, which is just the maximal spectrum. So this is the associated variety. Of vertex algebra V. Well, and of course you can ask if there is a possible way how to go from some Poisson algebra to vertex algebra, and this is called usually quantization. And of course, it is extremely hard how to assign to a Poisson algebra some vertex algebra such that the corresponding C2 algebra it's given Poisson algebra. And of course, there is a relation between these two algebras, as was mentioned. So if original vertex algebra it's positively graded, then it gives rise to some grading on this Jou's algebra. So you can take the graded algebra, which is again Poisson algebra, and you will get mapping which goes from Jou's C2 algebra to graded version of this Jou algebra. And this mapping is in general, it's a just surjective mapping, and it's a morphism of Poisson varieties. Poisson algebras. And it's not an isomorphism. In general, it's just surjective mapping. So, and then I need to briefly recall what is affine vertex algebra, because I need a little bit different notation. So I will take some graded, reductive algebra, and the level will be not an integer, but will be a some G invariant bilinear form on this algebra G. So if I have these data, I can consider the corresponding affine Kac-Moody algebra, which is just the one-dimensional central extension of the loop algebra. So the element C is central. Central element and the bracket. So if I just write using these modes AN and BM, it's just commutator of AM m plus n plus, and here is this evaluation of this bilinear form times delta. And if I have this affine Kac-Moody algebra, so I can assign the corresponding universal affine vertex algebra. So it's just, as a vector space, it's just generalized Varma module induced from one-dimensional representation. So here is the loop algebra or current algebra plus this central element. And the action of the central element on this one-dimensional representation is by 1, so C acts by 1 on. So, and then I can also take the simple quotient. So this will be the simple affine vertex algebra. So now I can at least give some examples. Well, in this case, well, for universal affine vertex algebra, this Jou algebra is just isomorphic to the universal enveloping algebra. Jou C2 algebra, it's isomorphic to the symmetric algebra, and the corresponding associated variety, it's isomorphic to the dual of Lie algebra G. So it's a Poisson variety. So what are examples? Some examples are, or some more interesting examples of associated variety for some simple affine vertex algebras. So associated varieties. So there are some well-known examples. Well, instead of generic or general reductive Lie algebra, I will consider just the simple. So from now on, G will be a simple Lie algebra. And Kg will be the Cartan-Killing form. And I will also need another Belinar form, which will be just properly normalize the Cartan-Killing form, and this HV is the dual Coxeter number. And K will be some level, so some G invariant, symmetric Belinar form. On G. So, and because it's simple, the algebra, so any invariant Belinar form can be written as a multiple of this K0. So K will be some complex number. So what are the known cases of associated varieties for some simple affine vertex algebras? Oh, so if the level is generic, so then the associated variety is just the dual of G. By generic, I mean that that universal affine vertex algebra, it's simple. So K is just isomorphic to K. And levels for which it's simple, it's due to Gorelick and Katz. So we know for which levels this is the universal affine vertex algebra. It's simple. And then the other level, it's critical. So in this case, the associated variety is the whole nilpotent curve, or I can write it's a regular orbit, it's closure of the regular orbit, but it's like dual, or by star I mean the corresponding subset in this G star, because it's co-adjoint orbit, closure of co-adjoint orbit in G star. So critical means that K it's equal by minus HV, this minus the dual Coxeter number. And the last class, well known, it's admissible level. So then, as was described in the previous talk, so it's some closure of some nilpotent orbit, and again, it's the corresponding subset in the in G star. So this is due to Arakawa. And admissible, yeah, this is some condition that K plus it's HB, it's P over Q, and plus some other conditions, and PQ are integers. So, but what other cases? So there is plenty of non-admissible levels. So what can we say about these levels? So I mean non-admissible, non-generic, non-critical. So for G, I will take some triangular decomposition. So H is a Cartan subalgebra, some Cartan subalgebra. And H plus N is a Borel subalgebra. Oh, and I also need some parabolic. So P will be a parabolic subalgebra of G, and I will suppose that it contains the opposite of this Borel subalgebra. So it will contain n bar plus H. So for this parabolic subalgebra, using this parabolic subalgebra, I can construct another triangular decomposition. So this is P, and this is Levy decomposition. So P is equal U bar plus L. This is the Levy decomposition. And L is a Levy subalgebra, so of P. Then to construct some. Sorry?
Your ends have changed here, right? This is with respect to your.
Once more?
This is with respect to your parabolic decomposition.
Yeah.
Your end here is different than your end above.
Yeah.
Okay, good.
So then I need to put some geometry. So to the algebra G, I can assign some group. So it will be a connected semi-simple algebraic group. And P will be some connected parabolic subgroup. of G. So if I have group G and parabolic subgroup, I can consider the generalized flag variety, so which is a smooth variety. And I can also consider another variety, which is G over commutator subgroup P if P. So this is usually called the generalized base affine space. And now if I take a weight, so which will be some special weight, so it will be individual of the center of the levy, so which is the subset of dual to the Cartan subalgebra, then a weight I can assign some twisted sheaf of differential operators on the flag variety. So this will be G equivariant sheaf of twisted differential operators on the flag variety X. And because this sheaf is G equivariant, so then it means that it's possible to construct a mapping going from the universal enveloping algebra to the global section of this sheaf. So, and this mapping is surjective. And I can do the same for the generalized base affine space. So on this generalized base affine space, I will consider just the usual sheaf of differential operators. So it's not twisted. It's again G equivariant. So G. So and again, because it's G equivariant, I will get a mapping going from the universal enveloping algebra to the global section of this sheaf. And what will be important for us, if I take the kernel of this mapping, so it's intersection of kernels of this mapping phi x lambda over all for all lambda, and this dual to the center of the Levy subalgebra, and this is also equal to intersection of annihilators of generalized Verma module with highest weight lambda. So this is generalized Verma module. So, and of course, because its intersection is phi y, its intersection of some annihilators. So this is a two-sided ideal. So then to this two-sided ideal, I can assign the corresponding associated variety of this two-sided ideal. So it will be and this is what is closure of Dixmier sheet. I don't want to give proper definition of the Dixmier sheet, but well, there is one possibility how to define Dixmier sheet. So if I have a parabolic subalgebra, then I can say that Dixmier sheet associated to this parabolic subalgebra is just this invariant subset. So I can take commutator of these parabolic subalgebras, take a complement with respect to Cartan-Killing form, and take the regular part of this subset, and then the closure is just, if I forget the regular part. So this is Dixmier sheet. What is important that it's not inside this Dixmier sheet, it's not inside the nilpotent cone. It contains some semi-simple element. And what is also important that Dixmier sheet contain.
Excuse me?
Yeah?
What is the notation SP star? What do you mean?
Well, this just means, so this Dixmier sheet is subset of G. So then I need, so this exactly is subset of G star. So then I put, so this just means that I identify, or I use the Cartan-Killing form to transfer this subset to the, to G star. So that's only the identification. And this Dixmier sheet contain nilpotent orbit, so which is called Richardson orbit. So, and closure is just, if I forget the reductive part. So this is the Richardson orbit. So now I will use this mapping UG. So this mapping phi x lambda. So which goes from universal enveloping algebra to some global sections, this equivariant sheaf. And if I restrict to some open subset, so there will be a restriction. So this is an open subset. Subset is usually called big cell. And it's, in fact, it's exponential of this u bar times b as a times p as a subset of x, which is just g over p. So it's an open subset. So, and in fact, I can get a mapping going from universal enveloping algebra to Weil algebra. So this is Weil algebra of a vector space, of the vector space U. So it's usual Weil algebra generated by partial derivative with respect to some linear coordinate functions. So, and now, if I have a mapping going from the universal enveloping algebra to the Weil algebra, I can do chiralization. So I can suppose that these are some Jou algebras of some vertex algebras. Well, in fact, it was done by Fagin and Frenkel. So we know that instead of UG, we can take the universal enveloping algebra. Then instead of Weil algebra, we can take Weil vertex algebra, or what is called beta gamma system. So this is Weil vertex algebra. And in fact, we have mappings going from UG to this Weil algebra, but it depends on lambda. So instead of taking for any lambda, so if we want to take for any lambda, so we can consider something what is called universal sheaf of differential operators. So this lambda, it's some kind of variables. So then this mapping goes from universal enveloping algebra for G to Weil vertex algebra, but then it's necessary to add some Levy algebra. So affine vertex algebra for the Levy, and then it's not at level k, but it's necessary to shift this level by some other level, and this is some p invariant bilinear form. So it goes from p times p to c, and it's defined. It's minus 1/2, and trace over G over P, and here is adjoint mapping for A and B. So it's some bilinear form on parabolic subalgebra P. So we can also restrict to Levy subalgebra L. So there is a shift. So, and this is the Feigin-Frenkel homomorphism. So which depends on the level K. And now I can do something interesting, because so I have this mapping going from the universal enveloping algebra to tensor product of these two vertex algebras. To the level but sometimes I can choose a level in such a way that is K minus KC, KCP, if I restrict on the semi-simple part, that it's 0. So there will be, so I will have an assumption. So I will have parabolic subalgebra. So P will be a parabolic subalgebra such that U is a commutative. So this will be first assumption, and second, for the level will be such that K minus this critical level for the parabolic, if I restrict on the semi-simple part, that is 0. So always, of course, it's not possible always. So if I choose some parabolic subalgebra, so sometimes it's not possible to choose a level in such a way that this is satisfied. But if this is satisfied, then I can construct a mapping. So there is a project. So I will have a mapping going from L to K minus just for the center, and this critical level, if I restrict to the center, so it just minus 1/2 of this adjoint of this Cartan killing form. So in fact, this is so this is K plus 1/2 of K kg. So, and why this is important? Because now so we have mapping this Eigen-Frankel, so it's, I will denote as, okay, so the tensor product of wild vertex algebras times k plus 1/2 kg for the center. Now you can apply this Jou functor so to get Jou's algebra. So first you will get the usual one, so you know there is a universal enveloping algebra. For this you know that it's wild algebra times, and here you will get just the universal enveloping algebra of Levy. And here you will get a mapping. And the same you can do if you do for the other functor to get this Jou C2 algebra. So, yeah, for this other, so it will be symmetric algebra, and here you will get just polynomials on this U plus U star, so U times symmetric algebra of the center, and in fact this mapping will be just the graded version of this mapping. So because this is homomorphism of vertex algebra, you can define the quotient vertex algebra. So I can take universal affine vertex algebra over this kernel of this Eigen-Frankel homomorphism. So, and the question is, what kind of vertex algebra is this? So, and what is this level? Because I didn't specify what parabolic subalgebra is it, and what level is it. So, and from these two commutative diagrams, you will immediately get that the Jou algebra of this quotient, it's isomorphic to the universal enveloping algebra over some ideal, and this ideal, it's exactly kernel of this mapping phi y, so which is intersection of these annihilators of generalized Verma module. So which means, yeah, so that's first result. And to get information about the associated variety of the corresponding vertex algebra, so yeah, so we can use the fact that the mapping, the canonical mapping from this for this vertex algebra, and G, which goes from this Jou C2 algebra to graded algebra of Jou, this algebra. In general, this mapping is just surjective mapping, but it's possible to show that this is an isomorphism. So which means that from this we immediately get because we know that the associated variety of this two-sided ideal, as I said previously, so it's isomorphic to closure of Dixmier sheet, and because of
This was a question in Anna's talk.
yeah.
But Anne claimed it for the reduced part of these rings, not for the algebras themselves. So you're making a stronger statement. So you're claiming that the associated gradient of the Joux algebra is isomorphic to the C2 quotient without taking reduced part.
No, I'm saying that for this special case, that this mapping, which is in general is just surjective mapping, but I'm saying that in this case, it's an isomorphism. Okay, yes. You mean this one?
No, that isomorphism that you're claiming there. So I asked the question during Anne's talk, and she was taking the reduced part of these rings. She was quotienting nilpotence, which you don't seem to be doing.
No, this is the associated variety of of this ideal. So I mean by maximal spectrum of this ideal. Oh, okay. So yeah, okay.
Okay, so you're claiming the same as Anne then.
Yeah, okay, yeah. So just reduced part. And yeah, from this, because this is isomorphism, and we know what is the reduced part of the associated ideal. So we will get immediately that the associated variety its closure of a Dixmier, of some Dixmier sheets. So when the question is what are these levels and what are these vertex algebras? And of course, other question is if this quotient is simple. So, and the answer is that in some cases it's simple. If it's not simple, that we can get information about the simple quotient. So we will get the following. So the first assumption was, so G is some simply algebra, and P is a parabolic subalgebra such that this U is commutative subalgebra. So there is a first restriction. So there is some well-known list of parabolic subalgebra such that this neo-radical is commutative. So that's first step. And second, we can easily compute what is the level such that if we restrict to the semi-simple part, then it's 0. So I will exclude this A1 case because this is not interesting, because then Levy part, we have to take Borel subalgebra, and Levy part is just, semi-simple part, there is nothing, so there is no restriction. And for SL2 we know everything, so we don't need to care. So this is algebra G. So then there will be level, and then what is the associated variety of the, I will write what is associated variety of the corresponding simple quotient, but I need to say how to prove it. So minus some of these cases were already proved by Arakawa and Moreau, but in fact, if you look at the proof, it's like case by case, and I don't know if, it seems at first sight that there is no relation between all these cases, but there is some relation. So so it's for odd and odd. Odd, even, and there is E6 and E7 minus n minus 2 minus 1 minus n half minus 2 minus n minus 4 and minus 6. So all these levels are non-admissible, non-critical, non-generic. So in this case, the associated variety, it's some Dixmier sheets closure. By P alpha 1, I mean parabolic subalgebra associated to the root alpha 1. So you omit the first root, and the other roots will be the generated Levy subalgebra. So this is SP. Okay, so this is some closure of some nilpotent orbit. So this was already known. So this is for n equal greater than 3, and for 2 it's just some Dixmier sheet. This is for n2. Then the Dixmier sheet, this is minimal nilpotent orbit. No. C. Sorry, there are one case is missing. So yeah, for D at level minus 2, it's minimal nilpotent orbit. Then you can consider Dn at level 2 minus n, and for even case at the same level. So if it's odd, then you will get again some Dixmier sheet closure. If it's even, then you will get some nilpotent orbit. So this nilpotent orbit is given by some partitions. So, and for E6 and E7, minus 4, minus 6. And for E6, it's again some Dixmier sheet. And for E7, it's nilpotent orbit. Oh, there is some classification, and in this classification, it's
I just
denoted
have
by
one
2A.
question.
Yeah.
So I guess when it's nilpotent orbit closure, it's not a consequence of your result.
Well, no. I'm saying that we will, by this, we were able to get some quotient. And for this quotient, we were able to show that the associated variety is the Dixmier sheet.
Yeah.
I'm not saying that the quotient it's simple. That's another question.
Ah, okay.
That is for simple quotient. I'm not saying that this quotient is simple.
Ah, okay.
So we need to show that sometimes it's simple, and if it's not simple, how to extract information about the simple quotient. Yeah, so some of these cases are known. So this is due to Arakawa and Moreau. So I think this one, this is known, this is known, this is known, this is new, this is known. This is known, this is also known, and these are new.
This now exhausts all cases. Now we don't just write for all possible levels or something else.
Well, these are some. Well, there are like two classifications. One classification for non-admissible level relates to the fact if the associated variety of the simple quotient it's minimal nilpotent orbit. That's done. And there are other cases.
A very naive question that are a little bit lost. So what is the final outcome? Now if I give you the simple quotient of the affine Katsumuni at any level.
No. That's in general it's unknown. So these are just,
Levels, right? So these are only Wakimoto type realizations of the
yeah.
algebra.
So by this construction, we were able to get some examples of non-admissible levels and associated variety of the corresponding simple quotient. So, yeah. So interesting cases are when the associated variety is some nilpotent orbit, because these are non-admissible levels. Yeah. I think I don't have. Well, and well, at least I can say how to prove if these quotients are simple or not. So it's based on Drinfeld-Sokolov reduction for the minimal nilpotent orbit. So, well, one thing, if you look at these levels, so these are so-called collapsing levels for this minimal nilpotent element. So which means that if you take the corresponding simple W algebra, then it's not really W algebra, it's just some affine vertex algebra. So that's first fact. So what we used, this was classified by Adamovich and some others for the minimal nilpotent element. So, and then if we apply this Drinfeld-Sokolov reduction for the minimal nilpotent element on this mapping, so in fact we were able to reduce the given case to the case which is of lower rank, or sometimes it's just SL2 case. So at the end we were able, and because of the properties of this Drinfeld-Sokolov reduction, this functor for the minimal nilpotent element, we are able to say, if we know for lower rank case, then we can use the induction to get information about the higher rank case. So this was used to prove that at some point, for some cases, this quotient is already simple, and if it's not simple, then you can do a little bit more to get information about the simple quotients. So, but yeah, it's possible to do. And of course, there is a possible generalization, because instead of, well, there was an assumption that U is commutative. In fact, it's not necessary to suppose that U is commutative. The only reason was that we need at some point a little bit explicit formula for this Fagin-Fraenkel homomorphism, which is not known in fully generality. So there is a statement that it's possible to do, but there are not so explicit formulas. So that was the reason that we used that its U is commutative. Then we are able to find explicit formulas, and for these cases, we can describe all levels such that this is satisfied and get information about non-admissible levels. So, and I think I will stop here.
Audience in Zoom, perhaps they can ask. All right, so I have one. I'm not sure if I'm following what's going on here, but it seems to me that you're taking this realization in chiral differential operators of your generalized flag variety tensor with a Heisenberg algebra, and you're using this fact that you can reduce to the center because, well, that helps you.
Yeah.
That helps you understanding what's going on in terms of the associated variety once you realize your algebra inside of these chiral differential operators.
Yeah.
Okay, so now my question is, what happens if you don't want to restrict to these levels and just look at any variety where G acts? This should give you some realization, Wakimoto type realization. You can play with different varieties in such a way that this level becomes, this Heisenberg that you need to tensor by becomes commutative again. It becomes Heisenberg instead of an affine algebra.
Well, the reason why we use the fact, because then the kernel, it will be a little bit definitely bigger, because you can, because it's not going to this whole vertex algebra, but you can take some simple quotient. So we are trying to replace this one, this universal.
Right, so that one, it seems, my understanding of this is that realizing the associated variety where this extra factor that you need to tensor by to deal with the level is not a Heisenberg algebra makes it hard, because then you need to deal with this affine algebra.
Yeah.
That's why you're requiring this second condition, which is very restricted on the level, so that you actually have a Heisenberg algebra instead of an affine algebra.
Yeah.
Okay, so my question is, instead of taking the flag variety, how about taking just an arbitrary variety where G acts? So that allows you to act with G for a fixed level, but that level might not be in this list of 2.
Yeah, that. Well,
And then for any variety where G acts, you have such a construction for a one level, for one given level.
No, but the problem is that, okay, so you can write formulas like for the finite dimensional case. That's okay. But then you need to deform.
No, the algebra has. I mean, the affine algebra has a morphism to chiral differential operators on any affine variety where G acts. Is that statement that you're using? It's just that it has it for only one particular level. If you want to deform the level, you need to do these tricks. But if you don't want to deform the level, you don't impose 2, and you have such an action.
Yeah.
Is it not true? You're the expert there. Is it not true? Okay, so any other questions? All right, so let's thank the speaker again, and we'll resume in half an hour.